the title is Conditional Generation with a Question Answering Blueprint. And the way we're going to go is like left to right. So I have a couple of slides on what conditional generation is to make sure we all understand what I'm going to be talking about. And then I will explain what the blueprint is and what it does for you and why it's wonderful. And I should say this work really came out of COVID. During COVID, I was stuck at home, you know, awful, awful situation. We couldn't go anywhere. And once a week, I would speak with this team in Google London. And the child of COVID, research child of COVID, is the work you will hear now. OK, and there are way too many to list them on the slide. OK, now let's get started. I just want to make sure that everybody understands, because there's a lot of confusion about these language models. So we have unconditional language models, and this is sort of statistics one-on-one, the bread and butter of what a language model is. And normally, a language model will assign probabilities to sequences of words. That is its job. And now, because these sequences can be very long, we usually take the chain rule and we decompose this probability using the chain rule. And basically, what this rule does for us, it reduces the language modeling problem to modeling the probability of the next word given the history of preceding words. This is what unconditional language modeling does. And GPT-3, or any variant of GPT, let's say X, still acts this way. But they implement this model with a ginormous neural network with 175 billion parameters. But you don't have to use a neural network. You could just go and count these things. It's just that we don't do that anymore because the neural networks are so much better. OK, so this is an unconditional language model. And then we have conditional language models. And remember, I'm talking about conditional generation. So this is what I will be focusing on. So a conditional language model now assigns probabilities to sequences of words given some conditioning context. And again, as with the unconditional language models, we will again use the chain rule to decompose this probability. And so what we're going to be sort of estimating using our huge language model is what is the probability of the next word given the history of the previously generated words and some conditioning context, X. Okay? So examples of this conditional generation is machine translation. We have a sentence in French, and we want the input to be its English translation. Or we have an image, and we want to describe this image. Or we have one or multiple documents, and we want to produce a summary. Or we have some acoustic signal, and we want to do the transcription of speech. We have a question and multiple documents, and again, we want to find an answer. This is your typical search scenario, where we ask questions, and the search engine will come up with an answer, which could be a long-form answer. And we'll be seeing examples of summarization mostly as our prototypical conditional generation task. Now, to train these conditional models, here's the problem. We need paired samples of input. So in this case, let's say it would be one or multiple document, and output pairs, which in our case would be a summary. But this data does not exist in large scale. So you cannot find hundreds of thousands of input-output pairs. So what do? So the way we get around this problem in modern NLP is we sort of have some data, but we will not use it immediately. We will first initialize model parameters via pre-training. And the way pre-training works is we hide parts of the input from the model, and we train the model to reconstruct those parts. And this way, we build representations of language. And the parameter initializations allow us to build these sort of powerful NLP models, but also they give us probability distributions, which are useful because we can sample from them and use them to do stuff like generation. And if you don't know about transformers, this is the one thing that everybody is using. Can I see a show of hands? Have people heard of transformers before? Yeah, it seems like we don't do anything. People have stopped after the transformers. They don't actually play with new architectures. So, and these tools are popular. They are available. You can download them from Hugging Face, and everybody can play. Okay, so we have 3 types of these pre-training models. And again, there is somewhat a confusion about what these different architectures are. So we can have pre-training, so we let the very large language model loose on the web, and so we can have encoder-only models, which just learn representations, and BERT used to be one of these models, and we still use in NLP BERT. So it goes forward and backward, it gets bidirectional context, conditions on future. Then we have decoder-only models. This is GPT, or any sort of GPT variant, where you generate on them, but you really cannot condition on future words. And the problem with encoder, decoder, you have to have ways of actually forcing it to see your input. And people do this with prompts. But there is no mechanism to do this conditional generation. And then we have pre-trained encoder-decoder models like T5 or BART, where the encoder benefits from the bidirectional context, but also we have a decoder, so they are trained to predict the output. And I'm saying all of this because I'm going to use a particular type of model for the blueprints, and I want you to understand how it works. Okay, so the backbone of the model we will use is this T5 model, which stands, there is 5 T's: text to text, transfer, transformer. And the pre-training objective is this span corruption objective. So this is an encoder-decoder model. This is our pre-training objective. And they've done something very smart. They replace different length spans from the input with unique placeholders. I have an example. And then they decode. The decoder is supposed to decode out the spans that were removed. So if we take the original text here, "Thank you for inviting me to your party last week," we will just remove some spans, like "for inviting" and "last week." And our input now will be this input with the spans removed, and the decoder is supposed to predict "for inviting" and "last." And we sort of will go and randomly white out, if you like, some spans from our input. And so this model is trained with this encoder-decoder objective, and then it is fine-tuned. So we let this loose, it learns the representations, and then it is fine-tuned with some tasks in mind. And this T5 model has been fine-tuned with some data, so we change the parameters, such as machine translation, linguistic acceptability. This is this 𝐸 sentence. Every task is prefixed with some information. You can think of it as an instruction, so translate English into German. 𝐸 sentence means judge the acceptability of the sentence. Semantic similarity, so is the rhino grazed on the grass similar to a rhino is grazing in a field? This is why it's like the similarity is just to be 3.8, I guess, out of a scale of 5. And it has been also fine-tuned with the summarization objective. So once we've done all that, we are almost set. We have this model. It has an encoder-decoder objective. It is trained with conditional generation in mind. What can we do with it? Okay, one more slide. There is different settings here. You can have a smaller model, a bigger model, a very big model with 11 billion parameters. All the experiments that we did were with 3 billion parameters, which I want to emphasize, this is not a small model. 3 billion parameters is actually quite big for all purposes. And you can download them from Hugging Face, these models. So you can reproduce everything. There's also a variant called long T5, and this is a sort of supposedly better model that can take very long inputs into account. And all of these variants use some form of manipulation of the attention mechanism, make it a bit sparser, and so it can supposedly encode very long input. And you'll see we have very long inputs in the experiments. Okay, So assuming I have this model and I've pre-trained it and I want it to do something for me, so now let's think for a second, what do we want generation to do for us? When we build a system to perform natural language generation, what are the goals? So first of all, it doesn't happen in the abstract. You have a communicative goal. You want to find out something, or you want to write a story, or you want to summarize, so the user has some intent. But also you want the output to be faithful and attributed to its sources. So in the case of summarization, you don't want the model to like lying and telling you things that are not there. And in a hypothetical scenario, you also want to be able to change the generation and say, hey, that's wrong, go back and generate it again. And you may think this is OK. I mean, this has happened, but we are not there by far. So let's take a simple example, which is single document summarization. This is a BBC article that is given as input, and we have a one-sentence summary as output. One sentence. That's not difficult. I mean, it's a simple task. In 2020, they did this study, Mayne et al., and they discovered that only 27% of the time the systems were faithful. They did not have hallucinations, 27% of the time. Maybe it's a bit better now, but still, it's not 100%. And I would say it's definitely less than 50%. And you can see the red bits there. These are mistakes. So for example, it says the Titanic is to become the first UK country to sign a treaty to protect the wreck. Not a country, last time I checked. And of course, the more complicated the summarization task becomes, the more unfaithful and the less controllable our generation becomes. This is your typical search engine scenario. I ask a question, what is the Titanic known for? This is not a simple question. You have to actually aggregate several documents and produce an answer, because the Titanic is known for a lot of things. And here, of course, if you make up things, it could be a lot worse. Then moving on, there is this task of dialogue summarization. Very challenging. So the task is set up as following, and it's supposed to sort of emulate how a human conversation would go. So we have a transcript. We take here the Big Bang Theory, Season 4, Episode 11. It's the Justice League recombination. I don't know, are people familiar with the Big Bang Theory? I did not pick this one person, one brave man. So the Big Bang Theory, it's a sitcom. It is very well known in America. It ran for, I don't know, 20 seasons. The people started young, then died by the time the thing finished. Anyway, very successful. It's part of the data set. We didn't pick this. But the task is you take this very long script of the dialogue in the series, and you have to summarize it. And I'll just read out for you the first couple of sentences to see how difficult the task is. Blue here denotes different protagonists, different people in the episode. So Penny starts dating Zach again. We have to know who Penny and Zach are. And since you haven't watched this, this is very difficult for you too. Used to being the target of bullying, Leonard, Sheldon, Howard, and Raj instead bully Zach through their implications to him that he's stupid. A human has written this. Not fully realizing what they're doing until Penny points it out to them, the guys decide to apologize to Zach the only way they can. And it goes on and on. So this task is like very long input and very long output. And the model is supposed to understand what's going on and what the relationships are between the characters to be able to generate the summary. So progressive difficulty. OK, so but why, before I actually present you some form of solution, let's think a bit why these things happen. Why do we have hallucinations? Why can we not actually have good summaries? They're fluent, but that doesn't mean they're good. So the problem relies in how these models are trained and what they actually do. So we have an encoder that learns the presentations, and then by magic, we hope that it will output the task that we want, the output that we want. And there is this black box in the middle where, you know, and the bigger the models get, the bigger the black box gets, and we actually do not know what's happening. So, and people have realized this. We're not the first ones to deal with this. And there have been some solutions. For example, you may want to change the way entities are represented and have some memory. You have some memory where you go and look up entities. Another way is to change the decoder. You say, you know, if my decoder has no high probability on some words, just skip them. Another fashion would be to change the encoder, somehow deal with the fact that you have very long input and encode it hierarchically. And a third way, a fourth way, is to change the attention mechanism. And we heard in the morning, the talk did exactly that. They changed with their attention mechanism to be able then to explain why the model made the predictions that it made. And the final way is to introduce planning components. And planning is like this intermediate step that goes between input and output, and hopefully, as we shall see, gives you some ability to control the model and explain what it's doing. OK, so, but if you're playing the planning game, if you're saying, well, I have some input, I'm going to plan my output, and then I'm going to generate this, the question arises, what kind of plan will you use? What is your plan? And of course, I showed you several summarization tasks. We don't want different plans for different tasks. Ideally, you want a sort of plan for everything. So here's where we're drawing inspiration from linguistic theory. So there is this theory of discourse structure called questions under discussion. And this is a theoretical model of how people communicate. So a QUD is a partially structured set of questions which discourse participants are committed to resolving at any given point in time. And I'll explain. So when I am talking to you, you are trying to understand me. And what I am doing is, the theory goes, I'm anticipating your questions, and I'm giving you the answers. So my talk is an answer to the questions you might have. Now, a question, the theory says, is a set of alternative possibilities corresponding in some way to possible answers in the question. Now, the theory, of course, says that the questions are implicit. So the discourse contains implicit questions for each of the assertions made, which then we turn into answers. So we take inspiration from this theory that tells us that, you know, people communicate by answering each other's questions and anticipating their answers. And we're going to take this now and take these implicit questions and turn them into explicit plans, which are going to help us do summarization and conditional generation. OK, so I'm going to show you how it works first, and then I'm going to explain how it's done. So imagine you have a question here, what is the Titanic known for? And you have some input, which are all these documents that your favorite search engine gives you. Now, what the model first will do is it will actually generate the plan. And the plan is what we call blueprint, and it's a set of question-answer pairs. I'm going to tell you how we get these, but first, just see how it would work in action. So the plan for this case is what kind of ship was the Titanic, what line operated the Titanic, and how many ships did the White Star Line make, in what ocean did the Titanic sink, and when did the Titanic hit an iceberg. So you generate this plan, question-answer pairs, and then based on this plan, you move on to generate the actual summary, or in this case, the answer to the question. And you see the color in the summary corresponds to bits in the plan. So a pink line in the summary verbalizes a pink bit of the plan. Blue, blue, and so on and so forth. Now, have a look at this plan. Is it correct? Do people know things about the Titanic? Yes. Yes, very good. Somebody's paying attention. OK, and there is another mistake, which you will not know, and it is the White Star Line made 2 ships only, not 3. It's a mistake. But now, here's the beauty. If we see this plan, we go like, what nonsense is this? So first of all, I don't care about these are the contentious bits of the plan. So what a human can do is say, OK, how many ships did the white star line make? I don't actually like this. So let me remove this. And the Pacific, sure as hell wasn't the Pacific, so it was the North Atlantic. So I'm going to change it. And by the way, I also want to find out when the DiCaprio movie came out. So the human can add this. So now we have a new plan that we've edited, we've corrected, and we will go on to generate our answer. And the answer will be 100% correct and faithful. So the Titanic was a British passenger liner. First question, operated by the White Star Line. I don't care about how many ships it made. It sank in the North Atlantic Ocean after striking an iceberg during its maiden voyage. And the film starring Leonardo DiCaprio has popularized the disaster and its aftermath. OK, do we understand the idea? Yeah, the idea is cool, right? No, don't say that. OK, now, so I'll tell you now how we do this in the remaining time. How much time do I have? Where is 10 minutes? OK, 10 minutes. OK, in the remaining time, I'll explain. But the main idea is important. So, so the blueprints are intermediate planning stage, are an intermediate planning stage for generation. The claim is they reduce faithfulness errors, so they're more truth, and they can actually be controlled. And are better if you have very long output, like a very long summary, like the dialogue summarization task that I showed to you with these characters, Zach and Penny. Now, the question is, of course, where do these blueprints come from? Because data sets as we know them, and I've introduced them in the beginning, are input-output pairs. You know, the X and the Ys. There are no blueprints. So, of course, and this is like, if you like, the negative bit, we actually need to create the blueprints. And it's not trivial to create them. I mean, it is not difficult, but you need to think about it. So I will show you how the blueprints are created for a toy example. So the data sets have input-output pairs. In our case, the outputs are these summaries or long-form answers. So we will take these summaries, and let's say we take a sentence from the summary, and from this sentence, we will identify noun phrases and named entities. We identify them, and then we use question generation tools, which you can again download from Hugging Face, to actually generate questions and answers. Okay? And we will over-generate. We will generate many questions and answer pairs, and then we will filter them using some heuristics that are again based in linguistic theory. So one, for example, heuristic would be, that's not a heuristic that makes sense. You do some basic consistency. You know, if you actually generate a question and you don't get the same answer, if you actually use the question answering task, that's a problem. Your question is no good. So this is called round-trip consistency check. Another idea would be, so all these questions would pass. The other thing would be we want varied questions, questions that talk about different things. So if you have repetition in the question, that's again not good. So here we would get rid of the final question-answer pair. And also we want to remove repetition. So if you have overlapping questions, you would also remove them. And so, you know, you start with many question-answer pairs, you reduce them using heuristics, and then you order them depending on how they appear in the summary, and that's your blueprint. OK, and so you would get this blueprint for this article, which is on Shelby Mustang, which was a car. That was, you know, Ford had introduced it, and then Shelby American came. You don't want to know this car. OK, now, once, I mean, it's interesting. Once you start like playing this game and you read these things, I mean, you go like, what are people writing about? OK, so right. So I told you now we have the input, blueprint, output pairs. And so because this is more expressive, this is a representation that is more expressive, we can do cool things with it, and we can actually define different kinds of models, which I actually personally like, because I don't like the fact that we have a monopoly for one model. We should have many models and different things. OK, so The first model that we will do is actually a simple model, and it's the simplest model you can think of, and this is not a straw man, this is actually quite a strong model. So we have our input, our encoder encodes the documents, and the decoder then will do the following thing. It will first generate the plan, question-answer pairs, and then it will move on to generate the summary based on the plan. So the blueprint is part of the output. Now, can people think what is the main problem with this model? There is a fundamental problem with this model. So the blueprint is part of the output, which means that we are taking up useful decoding space with the blueprint. And ultimately, this model will not be able to output very long documents because the decoding length will be all used up. The second model is a multitasking model. And this model now disassociates the blueprint prediction from the summary prediction. So it's trained to generate an answer plan and the output sequence. And you see the answer plan here. So this is so one bit of the model will generate the answer and the summary, and another part of the model will generate the answer plan and the questions. And these are trained jointly. This solves the problem of the very long output, but again, there is no connection, no tight connection between the blueprint and the output. And the final model is an iterative model, and this is actually the model that makes most sense. So this will do generation one step at a time. And what this means is we'll have our input, and then I will be planning sentence by sentence. So here, I will first plan the first sentence, and this is the blueprint for the first sentence, and I will generate it. You can see here the blue color. And each bit corresponds to different parts of the blueprint. Once I generate my first sentence, then I'm going to go take the output that I've generated into account, condition on it. So I'm going to condition on this, plan the next sentence, generate, condition on this, plan the next sentence, generate, and whatnot. So I incrementally plan and generate, and I interface both of these procedures. And this is good because this means that I actually can generate as long a text that I like, because my generation is like sentence by sentence, rather than I'm just going to generate a very big sequence. OK, so I have many results. I'll just show you results on the last task, which is on this data set called 𝐸𝐚 of dialogue summarization, where the input is a very, very, very long transcript, like a book, and we are supposed to output a summary. And this task is quite hard. OK. Before I show results, I skip this, I want to sort of flag an issue. How do we evaluate the output of these models? We can get humans. You can pay, if you're very rich, lots of humans to assess your output. However, this is harder than it sounds, because the humans have to understand the domain. They have to read, in the case of dialogue summarization, huge books. So the community has come up with metrics to assess these things automatically. The metrics are all flawed in different ways. And now we find out that because the systems are so fluent and so good at generating output, the metrics are useless. So we have to go back and actually think of different metrics. So 𝐸𝐻 is an example of such a metric. It is based on the overlap of the output with a gold summary. So it is lexical overlap based. And it tells you, like, have you come up with the same words, basically, that are in the gold standard? And you can see these are these three data sets, and there is a sliding slope. The harder the data set, the worse the systems become. And 𝐸𝐻 cannot tell you much here. It can only tell you that these blueprint models are not doing very much worse than a model that has no blueprints. So long T5 is a normal model without any blueprints. E2E is the end-to-end model. Multitask is the multitasking model. And iterative is the one that iterates at every step. And you see here, this is the model without any blueprint. It is high, and it goes a bit down. Here, not so much. And the 𝐸₂ data set, it's up and down, and near 30. So what can you say? However, we have the blueprints, right? So the model actually outputs the blueprint and then the summary. Since we have more information, we can now check, does the summary follow the blueprint, or does the model hallucinate? So we can very simply see if the summary the model generated gives the right answers to the questions that are in the blueprint. We can treat this as a question answering task. And this is what this evaluation does. We ask the question, can the generated text answer questions predicted by the blueprint? And you can see here that in 𝐸₂, the difference between the two models in the dialogue summarization task is huge. And if you have an iterative model that actually plans ahead step by step, it can produce better summaries and better blueprints. Now, faithfulness. This is another automatic metric. Is the summary faithful to the input? Or does it hallucinate? You see here the different data sets are ranked in terms of difficulty. And in the easy one, faithfulness is great. It's in the region of 80. The middle one, it goes down. And then with 𝐸₂, which is this dialogue summarization, we're talking very low numbers. But note the difference between the iterative model and a model that doesn't have any blueprints. I want to show you some output, and then I'll finish. So this is an example of long T5. This is a model without blueprints. And I will read out to you the summary. And this is not handpicked. So 𝐸ₐ and Catherine, this is a CSI summary, a crime scene investigation. I don't know whether people watch CSI. It's like there is these CSIs, and they go in the world, and there's crime, and they collect evidence, and then they decide who did it. It's a whodunit, but very nice, because they popularized these forensic scientists. Anyway, so 𝐸ₐ and Catherine investigate when a man is found dead in the dumpster. They soon discover a lot more went on in the kitchen than cooking. That is wrong. The kitchen plays a part, but they don't discover anything about the kitchen. Meanwhile, Nick and Sarah are called to the scene for a double homicide. The victims are a husband and his wife, who were both in the process of selling off their records. Wrong. It's only the husband. Suspicion quickly falls on the wife's ex-boyfriend. No, it's the husband's ex-girlfriend. But the evidence increasingly points to the husband. So this is long T5, and now the blueprint output. 𝐸ₐ, Catherine, and David investigate when a man is found dead in a dumpster. Who's David? Ha! The model knew David is their boss. This is nowhere, I mean, I had to watch the episode, but correct. The man had been eating at a restaurant called 𝐴NT∞ Pretzels. Again, I thought the model hallucinated. The name of the restaurant is really 𝐴NT∞ Pretzels. And it's an extremely obese man. They discover that he ate himself to death, correct. Meanwhile, Nick and Sarah look into the disappearance of a husband and wife who are found dead in their home. So usually CSI episodes have like two plot lines, a main one and a secondary one. The model picked up the fact that we have these two plot lines. So there is the man who ate himself to death, and then there is the disappearance of the husband and the wife who are found dead in their home. Also missing is a record collection that the husband had been collecting. Also correct. They also discover that the wife's neck was slashed in the attack. This is true, the dogs did it, and she was slashed in the kitchen. That's why T5 thought a lot was going on in the kitchen. CSIs tracked down Missy Halter. Missy Halter is the girlfriend. This is her name, a woman who helped them find the records. So yeah, a bit better. So to finish, it says here, see the demo. It's not a demo. It's a video of a demo. So I think this kind of new idea of doing generation opens up possibilities for humans in the loop to control, to check, to generate more accurate output. In the future, it may be nice each question-answer pair to be grounded in the input, to go back in the input and say, this is where I came from. It will be even more explainable. You could treat the plants as instructions and use reinforcement learning. This is something we're looking at in this point at this time. And of course, another problem, how do these blueprints work across languages? It's fine if you do it for English, where there's all these question-answering tools, but what if I had Bengali or some other language? So this is, again, future work. I should thank you and pause for questions.
So we'll have 10 minutes for questions. There's people walking around with microphones, so just raise your hand if you have a question, and you will be assigned a microphone.
If there are questions, there may not be any.
Hi, thank you for your presentation.
Hi.
I wanted to ask, in the case of long T5, did you also look at maybe different decoding methods? I was wondering if, for example, beam search could have avoided some cases where the model started off saying, I don't know, wife instead of husband, and then just had to continue and keep on going with the lie, even though later on.
That's a good question, and I didn't get into the technical. All the models used beam search, all of them. So T5, long T5, T5, our models, everything has beam search. And despite that, of course, we could have extended the beam, but then it gets slower and it takes forever and whatnot. With an infinite beam, beam, maybe you could find this. But yeah, it's not like sampling, decoding. It's really beam search.
Thank you.
Thank you. There's a question here and a question there.
Thank you for the amazing talk and lively talk.
Too kind, too kind.
It was great. I wonder whether you can say a few words about the role of combining linguistic theory with learning. And human in the loop, you emphasized this, but it seems like a lot of the improvement comes because you also employ linguistic theory, symbolic knowledge, so to say, that we do have, and we don't need to rediscover from scratch by learning from others.
That's a very good question, and I think actually, contrary to what people believe, that we can just have these models and let them run loose, and they will discover things. If you are playing representation, so playing with representation, if you have discrete intermediate steps that do things for you, then these have to be embedded in linguistics. I mean, one could invent their own thing, but that doesn't make any sense. And there's all these theories that tell us they formulate the problem for us in a way that we wouldn't do it. Now, we had linguistic theory before, but I think for questions under discussion, the thing that I talked about, actually, I was aware, the people who invented this are in my department, like Hannah Rhodey and Craigie, whatever. They are in linguistics next door. And when I saw them 10 years ago give talks, I thought, it's impossible to do this because QA wasn't good enough. What has happened now is like all these tools are a bit better, a bit more accessible, so we can go back and actually realize these things a lot better. Yeah.
Thanks, Mirella. You made a lovely comment about the evaluation. All of those metrics are flawed. And summarization is an extremely context and purpose-dependent task. So what are we evaluating there?
That is a very good question. So in the paper, there is 3 pages of human evaluation, okay? Just in case people want to actually go.
Great.
Yeah, we did that. I mean, and as a reviewer, always people, papers without human evaluation, they get a 1 by default out of 5. Now, the problem with summarization is as follows. You cannot be doing, during system development, human judgments all the time. I mean, maybe Google can. Maybe, if you have, or OpenAI, if you have a department doing this, you cannot. The problem is that for summarization, it used to be terrible because everybody would use rouge, which it turns out doesn't even correlate that well with human judgments. It started by saying, oh, rouge correlates with human judgments. This happened 20 years ago when the systems are broken. Now the systems are fluent, so the humans are getting cleverer. The problem is, like, they don't dislike the summary because it's not fluent. They dislike the summary because it's lying. So there have been a few developments in the evaluation of summarization that I quite like. The first is that there's new frameworks based on question answering evaluation and using entailment that are learned metrics that people are using. And that's good. They give you, at least we have plurality. It's not only rouge. But the question you raised, I don't have an answer for, that summaries are different for different people. And how actually can you make sure that the summary answered your intent? If you are doing question answering, like if you have the Titanic problem, then yeah, you can say, was my question answered or not? But in this case of the dialogue summarization, did you talk about all the important characters? Did you talk about the relations? And the longer the summary gets, the more problematic it is, because then not even humans will be able to assess it, because the humans get bored, tired, and they're only humans after all. So yeah, lots of future work.
Some extrinsic evaluation, but that makes the story ever more
complicated. Yeah, yeah, that's right. Yes, yes.
Yeah, I have a question. Yeah.
Where are you?
Yeah,
hello.
Yeah, thank you for the talk. So I was wondering about the training data for the blueprint part. So basically, your model involves a two-part. One's question generation, and the other part is to follow the blueprint and generate the summary. So I was wondering, the second step, do you have training data for the second step, or do you use supervised learning for that even?
Yeah. So and I did not explain this. So for all the tasks, the training data is input, blueprint, summary. The blueprint we generate for all the data sets we have created, and actually it's available. You can just go and get the blueprints from the website. Now, what the model does, it fine-tunes with this new data, with the blueprints, and then goes on and generates this. So we don't train a model from scratch. We just fine-tune it with this blueprint objective. And there's these three models that I
Yeah. So my question is you have, for example, you have some 3 data sets. You have Go summaries, but the summaries maybe they do not follow your blueprint because generated afterwards.
So the blueprint is generated based on the summary. So we get the summary, and then based on this, we treat the summary as a context. And given this summary context, we generate questions based on the summary. So all the blueprints are based on the summary. And you are telling me now, OK, it's an automatic procedure, so some of the questions may not follow the blueprint. And this may be a bit of noise that we are happy to tolerate.
OK, thank you.
But generally, in the human evaluation, we saw that 80% of the time, the summary follows the blueprint it is generated. So it's OK, you can control it.
Yeah, thank you.
We only have time for a single question, if there is one.
Up here. Hello.
Yeah, thank you for your talk. Yes, you said that you can exactly tell the program how many sentences it will give you, so how many information it will give you, and how does it chooses which information.
I did not explain this. Yes. So you mean in the iterative model, how does it know when a sentence begins and a sentence ends? That's your question, right?
No. How does it chooses which information is more important? So which information comes first? So when you say you want to have 4 sentences, it may give you four informations about the topic, and maybe when there's 10 informations, then which information is given you first?
Yes.
Which information is more important?
Yes. We leave this to the model to learn, but you raise a good question, which is how does it pick this? So these plans are plans. So the blueprint tells you This is what you will talk about first, about what is the Titanic, then who made the Titanic. Third, so if you've seen enough blueprints, you learn the plan to order the information. And in fact, if you scramble the order, the model doesn't do that well for the plan. Now, what you asked about the length, we don't do anything with it. So the model actually learns to output the length on its own. The iterative model is the only one where you can tell it, keep generating, because it plans everything step by step. So it can generate something for 5 sentences, but it could do 10 or 20 or 15, because it doesn't have that limitation. Okay?
Thank you.
Let's thank the speaker again for the amazing talk.
Thank you, guys.